Happy Friday. Made it all the way to the end of week 6. It's pretty impressive stuff. When you really think about it. Damn. Morning. All right. Okay, so last couple days we practiced and finished up the Gaussian elimination and the Gauss-Jordan elimination to solve a system of equations using a matrix. Very tedious, very annoying. I fully understand that. I think it's annoying as well. But hopefully you got some practice in and work through some of those problems that I gave you. We're going to kind of move on to a few more matrix things. We really don't have that much left. So that's nice, actually. I think we have maybe like 3 more lessons left. So we're on a great track. Yeah, so let's go ahead and do it. All right, today we're talking about a couple key things. So the first is called a determinant. The determinant of a matrix. Determinant is used for a lot of different things. We'll talk about one specific application of it here. The notation that we'll use is either you can just say det of a, or you can write it like this, kind of like the absolute value bars. Either one of these is completely the same, completely interchangeable. It does not matter. I typically use this because that's just what I'm used to, because that's what most of my teachers and professors use whenever I learned about it, so that's what I'm more comfortable with. But this is also totally acceptable. An important piece of information is that you can only find a determinant for a square matrix. Right? If we have like a 3x5 matrix or anything that's not a square matrix, we cannot find the determinant of that. We can only do it for a square matrix where the amount of rows and columns are exactly the same. 3x3, 12x12, 4x4, 2x2. All right. So we also have what's called a singular matrix. So what does it mean to be a singular matrix? Well, if the determinant is equal to 0, then we say the matrix is singular. Okay, so that's how we know that a matrix is singular, because we calculate the determinant and we get 0. Okay, so what does that mean? Okay, so again, we know if it's 0, then we say it's singular. Now, if a matrix is singular, that means it has no inverse. Okay, so we're going to start talking about kind of the idea of an inverse of a matrix. Right, so these 3 things that I have highlighted here, and I will now circle. These are all equivalent. Okay? If one of these things is true, then all of them are true. Right? If one of them is not true, then all of them are not true. This is especially important if you're someone who's trying to take the AFA of matrices. One of the objectives is a very annoying objective that asks questions about the properties of matrices. All right, and that focuses a lot. One of the things is it talks about being singular or having an inverse or not, or the determinant being 0. So, how do we determine if a matrix has no inverse? Well, it's based on if it's singular. Well, what does being singular mean? Well, it's based on what the determinant is. If the determinant is 0, great. Then it's singular. has no inverse. But if the determinant is not 0, well, that means it's not singular, and that means that it does have an inverse. Okay, so the first way we're going to talk about, there's different ways to calculate determinant depending on the size of the matrix. So what's nice for a 2 by 2 matrix is we can just use this little formula here. All right, once we get to larger matrices, it gets a lot harder, but it's nifty for a 2 by 2 matrix that we can just calculate the determinant like this. So this is a 2 by 2, so what it means is AD, all right, so we multiply these two numbers together. BC, we multiply these two numbers together. And then, as it says, we subtract. So this product minus this product. All right, pretty simple. Just don't forget the minus sign. That's honestly one of the biggest issues that I see here. Right? Don't forget the minus sign. Right, so that's nifty. Let's practice it a little bit. So the determinant of B is, so I first look at the main diagonal. So that's 3 times 5. And then I subtract this other diagonal, the opposite one, so 6 times negative 2. Okay, so 15, 6 times 2 is negative 12, so minus negative 12, so that would be plus 12. Okay, so the determinant is 27. Great. Next up, is the matrix singular? Well, remember, being singular is based on what the determinant is. Well, this determinant is not 0. Okay. In order to be singular, the determinant has to be 0. Oops. Okay, so this is not singular. Exclamation point, because I'm mad. Does the matrix have an inverse? Well, wait, let me look back again. Well, if it is singular, that means it has no inverse. So if it's not singular, that means it does have an inverse. All right, we're not figuring out yet what the inverse is, but it does have an inverse. Okay, and we can determine both of these things because we got a determinant that's an actual number that is not 0. Now, it could be positive, it could be negative, it could be a decimal, it could be a fraction, but the point is it's not 0. So that's how we're able to say not singular, it does have an inverse. All right, same thing. So let's find the determinant of G. I'll use the other notation here. Or this is the same thing as saying determinant of G. That kind of looks like 6. All right. Either way, or we can use these like absolute value bars. So multiply this main diagonal, so negative 2 times 15 minus 6 times negative 5. Right, so negative 30. 6 times negative 5 is also negative 30, so minus negative 30 would be plus 30. Negative 30 plus 30, 0. Okay. Is the matrix singular? Well, the determinant is 0. So yes, it is a singular matrix. Okay, does the matrix have an inverse? Well, we know that if the matrix is singular, then and that means it does not have an inverse. And I'm so sad about it, because I really wanted that matrix to have an inverse, but unfortunately it doesn't. Oh well. I suppose I will live. I will move on. But it crushes me emotionally. Okay, so it's nice to be able to look at the number that we get for the determinant and then be able to figure out, does it have an inverse or not? It's pretty nice. Okay, so that's determinant for 2 by 2. Again, pretty basic. Just multiply these numbers minus multiply these numbers. It's cheese. So now let's use that so that we can actually figure out what is the inverse. Oh, wait, one more question, sorry. Given the determinant, find the missing entry. All right, so this is kind of working a little bit backwards. We're given this matrix F, except I don't know what this spot is. However, I do already know the determinant of F is 30. All right, so well, let's think about the determinant of F. If I were to go through and calculate it using the formula, I would need to do 7 times x, so 7x, minus 5 times negative 3. So minus negative 15, so that would be plus 15. And we already know that once we calculate the determinant, whatever this is, we know that it's going to equal 30. So let's just set it equal to 30. And then now I can just solve this equation. 7x plus 15 equals 30. So I'll subtract 15 from both sides. So 7x equals 15. Divide both sides by 7. X equals 15/7. Okay. So we can also work backwards. Maybe if we're missing a number, we say, what is it that's supposed to go here? Well, we already know the formula that makes determinant for 2 by 2. So 7x plus 15. We'll set it equal to 30 because that's what we know the answer is already. And then just solve. Okay, so an inverse matrix. Technically, this is a multiplicative inverse, but whatever. We just call it the inverse matrix, right? A matrix, when you do matrix multiplication, you get the identity matrix. Okay, that's what it means to be an inverse matrix. Right? If you do matrix multiplication, you get the identity matrix. Now, the identity matrix, remember, is the thing that has ones down the main diagonal and then zeros everywhere else. Okay, the identity matrix is like the matrix version of the number 1. Okay. So the notation that we use, just like for functions, like we'll do f inverse of x, that represents, that little -1 represents the inverse. Okay, so same thing for matrix. Instead of having a matrix A, we'll have A to the -1st, which represents A inverse. That's how we would say it. All right, so matrix multiplication, we know how to do matrix multiplication. If we do A times A inverse, we should just get the identity matrix. Or if we even do it the other way, if we do A inverse times A, we should still get the identity matrix. Okay, both ways we end up with the identity matrix. Right, that's what it means to be an inverse. All right, so again, finding the inverse of a matrix is actually a pretty complicated process, but for a 2 by 2 matrix, it's a lot easier, so that's kind of nice. That's why we're starting with this kind of smallest square matrix, 2 by 2. So to figure out the inverse matrix. So if I have A, B, C, D, A inverse can be found by doing 1 divided by the determinant of A. And that is, we use scalar multiplication of whatever this is times this matrix. So note what happened. A and D just switch spots. Okay, A and D switch spots. B and C stay where they are, except we add a negative sign in front of them. Okay. So A and D switch places, but don't have anything to do with a negative, positive, changing, whatever. A and D just switch. B and C stay where they are, but we introduce a negative sign for each of those entries. And then in front we have our 1 over the determinant of A. All right, so actually pretty nice. Okay, so find the inverse and check to make sure it's correct. So how do we do that? Well, I'll show you, but let me paste this over so we can look at it. All right, so we have a matrix S, 1, 2, 3, 4. And I want to know what is S inverse. Okay, well, the first thing that I need to do is figure out what is the determinant of S. So that's, remember our formula, so that will be 1 times 4 is 4, minus 3 times 2, 6, so negative 2. Great. So let me now just follow the formula. So the formula says 1 divided by the determinant, so 1 divided by negative 2. And then for the actual entries of the matrix, right, just swap A and D. So 1 and 4, I'm going to switch those places. So now it becomes 4 and 1. And then for the 2 and 3, I'm going to leave those where they are. I'm just going to put a negative sign on them. So instead of 2 and 3, I have negative 2, negative 3. Okay, so now let's do the scalar multiplication. So I'm going to multiply negative 1/2 by each of these entries. Remember, because that's what happens when we do scalar multiplication. We just multiply everything inside. All right, so 4 times negative 1/2, that would be negative 2. Negative 2 times negative 1/2 would just be 1. Negative 3 times negative 1/2 would be positive 3/2. 1 times negative 1/2 would be negative 1/2. All right, so this is my inverse. But like I said, let's check. Let's actually make sure. Did I actually do this right? And what does this really mean to be an inverse? So my original matrix is 1, 2, 3, 4. Right? And I found that my inverse is this thing. Negative 2, 1, 3/2, negative 1/2. All right, so I'm going to do matrix multiplication here and see what I get. So remember, matrix multiplication starts the rows of the first matrix times the columns of the second matrix. So row times this first column. So 1 times negative 2 is negative 2. Well, actually, here, I'll just write it out. 1 times negative 2 plus 2 times 3/2. All right, and the next spot would be the first row with the second column. So 1 times 1 plus 2 times negative 1/2. Now I move down to the next row. So this row, the second row with the first column. So 3 times negative 2. Oops, can't really see that. Plus 4 times 1. And then the second row with the second column, 3 times 1 plus 4 times negative 1/2. Okay, so let's do some quick calculation. This 2 and the 2 would cancel. This 2 and this 2 would cancel. 4 and 2 would cancel to just leave me with a 2 there. Wait a minute. Oops. This was supposed to be 3/2. Right, this spot came from doing second row with the first column, so 3 times negative 2, but then 4 times 3/2 it should be. That 4 and that 2, so just give me 2. Okay, so negative 2 plus 3, that's 1. 1 plus negative 1, that's 0. Negative 6 plus 6, 0. 3 plus negative 2, 1. All right, and look at that. That's the identity matrix that has 2 rows, 2 columns. So that's exactly what we should get since this is an inverse matrix. Or since we multiplied a matrix by its inverse, we should always end up at the identity matrix. So it's a good little check that we can do if we're not certain that we're doing things correctly. All right, let's practice another one. So find the inverse. Okay, great. So the first thing I need is the determinant. So that would be 10 times 13, 130, minus 11 times 7, 77. That would equal 53. Is that right? Yes, 53. All right, so my formula is A inverse equals 1 over the determinant, so 1 over 53. All right, and remember our pattern. So A and D, 10 and 13, just switch places. So 13, 10. 11 and 7 stay where they are, right? B and C stay where they are, but they just get a negative sign introduced, so negative 7, negative 11. And now I'll just do the scalar multiplication. So 1 over 53 times all of these numbers inside. So 13 over 53, negative 7 over 53, negative 11 over 53, 10 over 53. And there we go. That's the inverse. And it's kind of, it's kind of worse. There's a weird fraction, but this is the inverse. If we did A times A inverse, we would get the identity matrix. Or if we did it the other way, if we did A inverse times A, we would get the identity matrix. Guaranteed. Promise you. But you can go through and check it for sure if you want. Okay, so just a couple simple formulas. Right, so determinant, multiply these, minus, multiply these. Inverse, 1 divided by the determinant. Switch these places, put in a negative for these places. And then remember our properties. So actually, let's just go back to these that we did. Right, if we think about our properties from earlier, we got the determinant is 53. So if the determinant's not 0, then it's not singular. If it's not singular, that means it does have an inverse. Right? That's why we're able to find the inverse here, because think about this formula. If the determinant is 0, then that means in our formula we're doing 1 divided by 0 out in front. Well, we can't divide by 0. So that's kind of one of our intuitive reasons we can think about, well, why is it that if the determinant is 0, that means it does not have an inverse? Well, it means we would end up dividing by 0 in our equation. So how would inverse be different if there was not a 2 by 2 matrix? Good question. That'll be our next class that we go on to talk about 3 by 3 determinant. But it's a much more complicated process, unfortunately. It kind of sucks. Determinants of matrices, even just going up by 1, right? Going from 2 by 2 to 3 by 3, it gets a lot worse. And then from that, going from 3 by 3 to a 4 by 4, it gets a lot worse. Then to a 5 by, just one step up, and it gets gross fast. The 3 by 3 determinant still it's not that bad, but it's definitely more complicated than this little formula here. But we'll talk about that next time. So on Tuesday? I think that's Tuesday, right? I don't have anything more in this lesson, right? Yeah, we'll talk about that Tuesday. Oh, wait. Sorry. You were asking about inverse for a 2 by 2 matrix. Interestingly enough, 1, 2, 3, 4. So, Jacob, since you asked, what you can do, and this will work for any square matrix, you can set up your original matrix here and augment it. Remember, augmented matrix just means there's this bar right here with the identity matrix. And if you do your row operations to put this into reduced row echelon form, but also apply the operations to this, not just this here, but this entire row or this entire row, eventually this will change into the inverse. So since you asked, I'll go ahead and do it, and we have plenty of time. So let's imagine if we wanted to put into reduced row echelon form. We want this to be a 1. Okay, great. That's already a 1. We don't need to worry about that. So the next thing I would want is for this to be a 0. Okay, so what do I add to 3 to get 0? Negative 3. So I'll do negative 3 times row 1 plus row 2. So row 1 stays the same across the entire top. However, row 2, so negative 3 times 1 is negative 3. Negative 3 plus 3 is 0. Negative 3 times 2 is negative 6. Negative 6 plus 4 is negative 2. Negative 3 times 1 is negative 3. Negative 3 plus 0 is negative 3. Negative 3 times 0 is 0. 0 plus 1 is 1. Okay. All right, so I have a 1 and a 0 below it. That's great. I want to make the next diagonal 1. Okay, so how do I make negative 2 into a 1? Let's divide it by negative 2. So I'll do negative 1/2 times row 2. So row 1 stays the same again. 1, 2, 1, 0. 0 times negative 1/2 is 0. Negative 2 times negative 1/2 is 1. Negative 3 times negative 1/2 is 3/2. 1 times negative 1/2 is negative 1/2. Okay, and now I want, so I have a 1, 0 below it, I have a 1 down here. There's no more 1s to get, or there's nothing more below, so now I'm going to work on the upward stuff. So I want to get rid of this 2. I want to clear it, make it a 0. So what added to 2 makes 0? Negative 2. Great, so let's do negative 2 times row 2 plus row 1. Row 2 will stay the same. 0, 1, 3/2, negative 1/2. Okay, negative 2 times 0 is 0. 0 plus row 1, it's 1. 1 times negative 2 is negative 2. Negative 2 plus 2 is 0. Three 3/2 times negative 2. Right, so those 2's would cancel. It would just leave the negative and the 3. So 3/2 times negative 2 is just negative 3. Negative 3 plus 1, negative 2. And then negative 1/2 times negative 2. So the negatives would cancel, the 2's would cancel, so that would just leave me with 1. 1 plus 0 is 1. So it should be negative 2, 1, 3/2, negative 1/2. Yeah, look, that's the same exact thing we got here. Negative 2, 1, 3/2, negative 1/2. Okay, that's the inverse. And so this process, Jacob, will work for any size matrix. Now, I showed it just with a 2 by 2, but if I wanted to do it with a 3 by 3, where I have, 4, 2, 6, 5, 1, negative 1, 3, 3, 8, whatever. So if this is the matrix I want to find the inverse of, I augment it with the identity matrix, and then I use my row operations to put this into reduced row echelon form. As I do that, this right side will change into whatever the inverse is. Okay, and so that process will work with any size matrix, 3 by 3, 4 by 4, 5 by 5, as long as the determinant's not 0. As long as the matrix actually has an inverse, then doing this process will work. So it's pretty neat. Nice like rice, man. All right, any other questions? All right. Then I will see you guys back on Tuesday. And we will... What did I say we were going to talk about? Oh. We're going to talk about the 3x3 determinant. So we have our nice little easy 2x2 determinant formula. Let's crank it up to 3x3 and learn a little bit more complicated of a process. But that's fine. Whoa. What happened? Whatever. Okay. So have a great weekend, and I'll see you guys then. Peace.